we will be looking at the alien dictionary problem and build a solution in JavaScript using depth first search traversal. Before jumping into the solution aspect, let us first understand the problem statement. We will be given an array of words arranged in a sorted ascending lexical order, wherein we will have the alphabets in this dictionary using the same English alphabets, but the lexical order is going to be different. What do we mean by this lexical order? We know that in English we have A, after A comes B, then C, D, E, F, G, and so on. In this alien dictionary, the sequence is going to be different, and we don't know what this sequence is. So it can be B, D, E, A, or something else. We don't know the sequence, and the aim of this problem is to take these words as input, and because they are sorted in this ascending lexical order, from this order itself try to find out what is going to be the sequence of every unique alphabet that is going to be there. Just return the order in which this alphabet exists in this alien dictionary, and if we are not able to form this pattern of the lexical sequence, just return an empty string. And that's pretty much it in terms of the logic. Now let's see how we can try to reach a solution. Let's go by words that we are given. Now we have to note that if we just consider a single word, let's say the word that is given is WRT, from this itself I cannot make out what is going to be the lexical sequence. Why? Because this is going to be just relative. The words can be ordered in any manner because this is just a word. Like in English we have words that are not going to be very specifically in like the format of A, B, C, D, E, F, G. It's just going to be words like LeetCode or Sony or whatever. Now the thing is, what do we do if we are not able to use this as the starting point to find the lexical order? We use the words themselves and compare with each other to find which symbol or which alphabet is going to be coming first and which is going to be coming later. And how do we do that? Let's see, we have WRT here and we have WRF. So these are the first two words that we have. We will go comparing character by character or symbol by symbol. And to do that, we will just say compare this W with the W here. So the first characters we compare. If they are equal, just ignore them for now. Then we compare the next character or next symbol. Both of them are equal, so we just ignore them for now. Then we see the third character that we have. Here we have T and here we have F. Now we know that the first word is before and then comes the second word. Now if the first string that we have is same in both, that would mean that in terms of lexical order, T is going to come first and then it's going to be F. This is what we are able to determine when we compare two words that are given to us, provided that this is in a sorted lexical order. And the constraint here is, yes, the input that is going to be given of words to us, it's going to be sorted in an ascending lexical order of words. And from this we can build a graph, and that graph can be represented as a adjacency list for the sake of this example. So we will build a adjacency list. Why a adjacency list? If you ask, it is just a representation of the graph so that we can work with the graph and do a depth first search traversal. Why build a graph? We know that we have to return an output of the unique symbols in the lexical order. So if I keep on building this graph in such a manner that we keep track of which letter comes first and which letter comes afterwards, and then if I just traverse it in one sequence going towards from the start towards the end, then I will get that string. So what will this adjacency list consist of? We can start with W. We will see what is going to be the dependency for W. Then we have R here, we are going to see what is the dependency for R. Then we have T here, we see what is the dependency. What I mean by dependency is which is going to be the symbol that comes before this symbol on the left side. Then we have F here. Now we know that for F, T is going to always come before, and I can just represent it as something like this. So for F, the array is going to be having T in it because T comes before F. That's what this adjacency list is going to be representing, and that will mean that in terms of graph, I will have somewhere in the graph I will have F, and because T comes before, there will be an arrow going from T to F. Now whenever I build this sequence, I have to build it in reverse because then I will be doing a depth first search. Because of that, I will say F has a dependency of T, and I'm not saying T has F which goes from T to F. Because I have to come in a reverse manner, I'm maintaining it in the other sequence with the symbol and its previous symbol. And similarly, let's just proceed to the next words set that we have. So now we were able to set this. Next is after WRF, we have ER. So we will say ER here. We will compare the first words again. We will say W and E. So now we know that W is going to be coming always before E. That's a dependency. I will say E here and I will put W here. Then I will move on to the next R and R here because there is not going to be any change because they are equal. Now we will say we left out F. We will only be able to compare up to the minimum of the two strings or two words that are given, because then there is nothing else to compare. Either you can add it and try to compare, but that doesn't give us anything in this case. We will only compare until we have equal length in both of them to compare, and the rest we will just skip because this is the only input that we have to work with. After that, I will take next one, which is ETT. So I will say ETT. I'm just picking up words from this list that we are given as an example. I will compare E and E, it is same. I will compare R and T. So I know for T, the previous symbol is going to be R. I will put R here, and then I will just proceed ahead because I could only compare it to here. After ETT comes RFTT. So now I will compare E and R. That tells me E comes before R, and this will be in the adjacency list. Then I will see T and F. I will know that T comes before F, which is true. We have already found that out. Then we will compare T and T. It is going to be same. Now from this adjacency list, if I try to build a graph, how will that look? So let's see how that looks. I have W that doesn't have any prerequisite. This will be the root of our graph that we are building. And I will have W at the start. After that, I will have W is a dependency for E. After E, we will have R because after E comes R. Then after R, we will have T. And after T, we will have F. And this is the graph in this sequence that we were able to set up. Now we will just traverse this in a depth first search fashion, picking up every value at each depth of the iteration, which will give us basically W, E, R, T, F. And this is what we will be returning. And that's why we arrange them in a reverse list manner, because when we go from the top to the bottom, we could just pick up the values to form the lexical sequence that we want here to be returned. And that's pretty much it in terms of the whole logic. On this list, we will just do a depth first search, and we have to make sure that a cycle doesn't exist, because if a cycle exists, then we cannot really make out a pattern here. What I mean by that is, if I said that F was now pointing to my W, that will create a cycle, and if there is a cycle, I really cannot have a sequence because it will just keep on going in an infinite loop of itself. And that's why if we are able to detect a cycle, we will just say no, you cannot form a sequence of this lexical order. Now let's see how this looks in terms of code. First step is we want to keep track of the output that we are going to be returning here. And to do that, I will just say let output is equal to empty. And in the end, I will just return this output that we are building. Then we said we want to build a adjacency list, but it's going to be in this reverse fashion. So how to build this adjacency list of characters or symbols that we have in this alien dictionary. To do that, we can just say let reverse adjacency list be a map. So I will have a map against each symbol. What is going to be the dependencies? Which symbol is coming before that specific symbol? And I will also make sure to ensure that I trying to see whether I find a cycle or not, some kind of tracker. So that will be scene is equal to new map. This I will be using in the later half. First, I will just build the graph, and then I will use this scene to detect whether there exists a cycle or not. After this, I will build my HSC list. First, I will just put empty values in it, and then I will go through them, fill them up properly as I loop through my words by comparing the first and the second word, and then I will try to see whether a cycle exists. And that will look something like this. I will just say for let word of all the words that we have received as input for each word that is there. So let character of the word that you have, just set it in the map against the symbol, because this character is the symbol that we're looking for. And I will just say this list dot set whatever the symbol, against that I will set an empty array. Next step after this is going to be now filling these dependencies so that I can build the agency list that we saw earlier. And to do that, I will go from I is equal to 0 up till words dot length -1. Because why -1? When I reach the second last, I will just pick up the second last and the last to compare, because I cannot really compare the last one with something else out of bounds. I have to always compare two words that are given. So I will only to go to length -1. Then after I have built this loop, what now? We said we will compare character by character, and if the characters are not equal, then create this dependency. And to do that, I will just say while going through this loop, let's pick up the first word, which is basically going to be words of I. After I pick up the first word, I will just pick up the second word, which is going to be words of I +1. I have picked up my two words. So I picked my first word, I have picked my second word. After I pick my two words, I will go comparing character by character. So if the word 1 dot character at somewhere, now what is this going to be somewhere? I have to go in a sequence until the length, which is going to be the minimum length between these two words. What I mean by that is, when I have these three characters and I have these three characters, I will have to go all the way with this index up to 3 and compare character by character. And to do that, I will again use a loop. So I will say let j is equal to 0, j is going to be less than math dot minimum of the two lengths that I have received. So I will say word dot length and word 2 dot length. Out of this, whichever is the lesser one, just pick that up, because we always need two characters to compare. If you run out of characters to compare, you just end there and then move on to the next one. Now I will say if you have found what you are looking for. So what we are going to say is, if the words are not having symbols that are equal. When we had W and W, we had equal. When we had R and R, it was equal. When we had T and F here, they were not equal. So only if the characters that we have are not equal, character at J position is not equal to word 2 dot character at J position. In that case only, I will put this comparison, put it in my agency list, and I have found the order that I was looking for. After that, I will just break this specific iteration and move forward to the next one. And to do that, I will just say something like this. If I have found, then what do I do? I have to push it in the dependency of the specific symbol. And how do I do that? I will just say in this adjacency list that I have, I will first get the character which I have. So let's say I got my character T here, and this T is going to be a dependency for my F. Now F is going to be my word to character, and whenever I get the character, it's always going to be from word to, and then I will, in this array that I have received, just push the dependency character word, which is going to be from the word one string that I have received. So pick that character. In that case, what we will say is for F, we pick up T, which is going to be word one's this index that we have here, and just push it in as a dependency. And that's how we get this specific entry. For F, the dependency is going to be T. And that's the part of building the adjacency list that we wanted to build. Now, after we have done this aspect, we will just have completed the building of the adjacency list. What happens after this? So now you have the adjacency list ready with you. What next? After the adjacency list is ready, we have to now see in a depth first search traversal manner, keep going by node, pick up the values of the symbol that you have, and if there exists a cycle, just say no, you cannot have this. But before we do that, there is another catch we have to be careful about. We have to make sure that it is always going to be possible to form this sequence. Now, in what case you cannot form a sequence? Let's say if you have A, B, C, D as the first word, and the second word is AB. So you see that this word that we have here is the starting combination in my first word. And if this case comes wherein you have the first word starting with the second word itself, you really cannot have a proper valid lexical order. You have to just exit. And to do that, I will just say within my loop here that if the word one dot length is going to be greater than the word two length, and my word one starts with my word two, in that case we will never be able to have a proper sequence and we will just return empty. And after this edge case is being handled, we will now move forward to build the logic of doing a depth first search traversal, and that will look something like this. So I will just say do a depth first search traversal. If you detect a cycle, no, you cannot have an output, just return empty. And for that you will just pick a symbol. Now this symbol that you're going to be picking, we will first keep a track of it in this scenery. So we have now at this point build a reverse adjacency list setup that we wanted. We will work with this setup now because that's like a graph equivalent, and with this graph equivalent we will now traverse and see if I can see a cycle or not. And to do that, I will just say if within my scene map that I have, if this symbol exists, whatever the value of that symbol is there, just return that value. And if a cycle is going to exist, this will be false, or it's going to be true if there is no cycle. So this is for no cycle, it's true. And in the end I have to return something. So I will return true in the end if everything is fine. And before that I will mark this scene.set for this specific symbol as false, because I am going to go to its children now, the dependencies that exist, what is going to be the next symbol after my current symbol. And because of that, I don't want to mess with the flow of my specific iteration that I am currently at. And to do that, I will first set the scene as false, and afterwards, just before returning, I will set it back again to true. Now the part of jumping into its dependencies come into play. And to do that, I will just say for let next of what are the dependencies of this specific symbol, and the dependencies are going to be from the list. Just get for that symbol whatever dependencies we have, and then I have to iterate. So I will say if no depth first search for this next one, I will just return empty. And similarly here also, at the end, before returning my output, I will go through all the characters that I have in my adjacency list that I have built. So what specific characters I have is WRTFE. So I will go through each of them and do a depth first search traversal, and that will something look like this. Let the key of my adjacency list, I will just say if no depth first search for this key, just return empty. And I'm going to get false from this DFS if we see a cycle. That's what we said here, that if you see a cycle, you will be getting a false value, and if you get a false value, this becomes true, and then you just return. So whenever there is a cycle, you just say you cannot form this lexical order. And now the next step here is, the aim of the problem statement was we want to return a string. Now at this point we are not building the string anyway, we are just going and building the graph first. After we have built the graph, then we go on and do a traversal for each of the unique symbols that we have, because the aim again says we have to return all the unique ones in the sequence. We don't want to do repetitions. And at this point you say you set it as false, then you set the scene as true. What you have to do is append this value of symbol to the output to give you the correct sequence. So I will just say output plus equals whatever symbol I have received. And that's pretty much it in terms of the logic that we have here. We will go through this DFS, we will first build the backbone of the adjacency list, then we will build this reverse adjacency list, we will do a depth first search traversal, and we return. And in terms of the time complexity that is going to be involved here, what is going to be the amount of time taken will depend on this loop here to build the adjacency list. Now to build the adjacency list, what is going to be the amount of time taken? It is going to be the total number of words that you have, because in worst case you will go through all the words and keep comparing, and because of that, let's say the time complexity that is going to be involved is going to be big O of C, where C is the total number of characters in combination of all the words that you have received. So what I mean to say is we have like 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 words. So it's in this case C was 15, so big O of 15 in that case. And in terms of the depth first search traversal here, the time complexity is going to be depending on the symbols that you have, and as we have in English 26 characters, in this language also, because it's taking alphabets from English, it's also going to have 26 alphabets only, and this will be big O of 1 because you can go up to 26 alphabets at max. And if you find a cycle, we will exit midway somewhere. And that's why the overall time complexity that is going to be valid here is going to be big O of C, where C is the length of total words symbols that we have received. And in terms of the space complexity that we are going to have, that is also going to be big O of 1, because again for DFS we will say just keep on going through this the first search traversal in a recursive fashion, and we can go in this recursive fashion only up to the valid number of symbols that you can have, which is going to be a finite number. That's why the space complexity will be big O of 1, and that gives us, in terms of the additional space, is just this output, which is big O of 1. This map is going to be a linear fetch and storage, so that is also going to be big O of 1. That's why the overall space complexity is also going to be big O of 1. And that's pretty much it. Thank you for watching. Please like and subscribe.